So, thank you. I will tell you something about tree graphs and unitary transformation between Hamiltonians on tree graphs and Hamiltonians on half-lines, and then I will use it to prove that under some circumstances there is no absolutely continuous spectrum for these tree graphs. This is joint work with Professor Exner, who is my supervisor. Well, first we consider radial tree graphs, which were shown before, and I will describe it later. Then we use unitary equivalence between Hamiltonians on trees and orthogonal sum of Hamiltonians on half-lines. This was first shown by Naimark and Solomiak, and later developed by Sobolev and Solomiak. But they proved this equivalence only for Hamiltonians which have Kirchhoff or free or Neumann coupling conditions on the tree, and we try to generalize their result for a much larger family of coupling conditions on the tree. Then this result by Sobolev and Solomiak was used by Breuer and Frank, and they proved that for tree graphs with Kirchhoff coupling conditions which are sparse in some sense, there is no absolutely continuous spectrum. And again, we generalize their result for some part of this large family of coupling conditions. So we use rooted tree graph, which is matrix and which is infinite. Part of it is shown here. We denote the root by O, and by K we mean the generation of the vertex. The vertex is in generation K if there are K minus 1 vertices between the root and the vertex. So, for example, this one belongs to generation 1, these 3 vertices belong to generation 2, and so on. By branching number, I mean the number of edges which emanate from the vertex. So the branching number for this vertex is 3 because 1 edge goes into this vertex and 3 of them emanate. By a radial tree graph, I mean the graph where branching numbers are the same for all vertices from the same generation. So for these 3 vertices there are the same branching numbers, and the length of the edges which belong to the same generation are also the same. So here our Hamiltonian acts as minus second derivative plus some potential. The potential is real, bounded and measurable, but it depends only on the distance from the root, so it is symmetric in some sense. The domain of our Hamiltonian consists of functions which belong to Sobolev spaces and satisfy the coupling conditions. The coupling condition at the root is described by this equation. It is general coupling condition which is Robin, and the parameter of this coupling condition is theta 0. More interesting are the coupling condition at other vertices, and these coupling conditions are described by these 3 equations. The first 2 represent the coupling condition in the subspace, which is in some sense symmetric or radial. By radial functions, I mean the functions which do not change if you exchange two subgraphs which emanate from the vertex. So these functions are in some sense symmetric with respect to the vertex. So these two equations describe the coupling in the subspace, and the third one describes the coupling in its orthogonal complement. The first two equations have four real parameters because alpha and beta are real, gamma is a parameter which is complex. And the third equation is described by this matrix UK, which is unitary and which is b minus 1 by b minus 1. And here the matrix V is b times b minus 1 matrix, and it is orthonormal, and the rows of this matrix are perpendicular to the row which has ones. Yeah, so this matrix maps the vertex of functional values which emanate from the vertex and the derivatives to the subspace of orthogonal complement of these radial functions. So what is important is that our coupling conditions do not couple the radial subspace and the non-radial one. So we have four coupling conditions given by alpha, beta, and gamma, and b minus 1 squared coupling conditions in the non-radial subspace. So we describe this family of coupling conditions. But as we will see only the eigenvalues of UK influence spectrum. Well, we have to suppose also that coupling parameters are the same for the vertices of the same generation. Well, I will show something about point interaction on the line to show why we chose the coupling conditions in the way I showed you before. We have two different parameterizations on the generalized point interaction on the line, which are described by four real parameters. The first one uses alphas, beta, and gamma, and for example, you can easily describe the delta condition if you choose beta equal to 0 and gamma equal to 0. Also, the Kirchhoff coupling conditions is easily described by taking alpha, beta, and gamma equal to 0. The second description doesn't cover this case, doesn't cover the case where beta is equal to 0. So that's the main disadvantage, but in some sense it has advantages, and formulae are prettier in this description. So let's go back to trees and to mapping conditions in the radial subspace to the half-line. We use two isometries. The first one maps the function which are in the radial subspace to the weighted subspace L2 R plus G0, where G0 is a branching function. You just obtain this function by multiplying the branching numbers up to the point. And the second isometry uses the square root of this branching function and maps the function to L2 on R plus. So if we use these two isometries, we obtain this mapping, and if we substitute it into equations of coupling conditions, we obtain these relations between the coupling parameters on the half-line, here, here, and here, and the coupling parameters on the tree. You can see that in the second parameterization the formulae look more prettier than in the first parameterization, but we need this parameterization to describe the case where beta is equal to 0. For example, this is also the case which was used in the paper of Proer and Frank. So in the non-radial subspace, we use unitary operator Rv for each vertex V, and this vertex maps the B functions which are supported on the subtrees emanating from the vertex V, and maps it into the subspace of non-radial functions. Here Vk was introduced before, and Wk is the square matrix which diagonalizes the matrix U. So using this operator we can decouple the functions in the non-radial subspace, and then we can construct the Hamiltonians H, B as radial, which consists of functions which under the action of this operator decouple and are supported only on the subtrees which emanate from the vertex V. And the coupling condition at the beginning of the subtree, at the root of the subtree, is given here, and in this coupling conditions there are parameters which are related to the eigenvalues of the matrix UK. Just to be precise, the eigenvalues of this matrix are e to I theta ks. So using this transformation we can prove the theorem that the Hamiltonian on the tree is unitary equivalent to orthogonal sum of Hamiltonians on the half lines. Well, this works that the symmetric subspace or radial subspace on the whole graph is equivalent to one half line. Then we use the functions which are in the non-radial subspace. For example, for this vertex we have two more functions in the non-radial subspace, so we obtain two more half lines which begin from here and go to the infinity and have here point interactions at t2 minus t1 and so on. And we proceed similarly for the vertices of the second generation. We have three more half lines and so on, and we can use it to prove the absolutely continuous that there is absence of absolutely continuous spectrum. I will not go into details since we don't have much time. The proof is very similar to the one used in Proer and Frank. We need sparse tree, which is tree when the sequence of lengths of the edges contains a subsequence which grows into infinity, and the proof holds for most of the coupling conditions of the family of coupling conditions I showed you before. But there are some non-trivial coupling conditions which have absolutely continuous spectrum. For example, if you have coupling conditions which you can map on the half line so that there are free coupling conditions on the half line, then Of course, you have non-trivial absolutely continuous spectrum, and you can also obtain purely absolutely continuous spectrum. But these cases are in some sense exceptional. So I will skip this part and show you only the assumptions we use. The first one is that the tree is sparse. Second one, that lengths of the edges are non-zero. And the third one has something to do with coupling conditions. It means that B is, there exists some constants delta and k, that beta is greater than delta and C is greater than delta, or beta is equal to 0, and you have some assumptions on gamma or alpha. Then if there is also at most finitely many coupling conditions which separate the half-line, then you obtain the result that absolutely continuous spectrum for the tree Hamiltonian is empty. Okay, thank you for your attention.
So I think that Professor Sonada is inviting us for a reception.
Not me, but the